My presentation today is about building resilience. And till about a year back, we used to call it building sustainability. And I think we sort of looked at not changing sustainability, but increasing the scope of sustainability to encompass many other factors which we used to think about, but didn't sort of analyze with the rigor that we were analyzing our buildings in terms of sustainable design. So India is one of the largest populations in the world, next to China. It's about 1.4 billion people. But urban India has all the sort of issues that large emerging nations have. It has water issues in our cities. Climate change has affected India tremendously. We've had some of the worst weather patterns in the last year or so. We've had issues with energy. We've had issues with pollution. And some of this led to a lot of our early thinking why we would pursue the whole sort of genre of sustainable design and see if architecture, if buildings, the whole built environment can help resolve what our politicians and what our cities over the years have not been able to do. So very early on, we sort of looked at what's really the issue with energy. And we did this study about a couple of decades back. At that time, India's population was 1.2 billion, and now it's about 1.4 billion. And just very broadly speaking, in terms of the fact that India has a daily solar radiation, which is on an average 5.5 kilowatt hours per square meter of the country's mass, we only really need 0.003% of this land mass if we were to just drive our entire energy by solar. It's actually nothing. It's only 2% of the wasteland, the deserts of India, is all that we would need to drive all the energy, not for today's requirement, for what is projected for 2050. And then the second part was water. And if you just look at the annual rainfall, I know this is very macro level data, but it laid the context of what we would do at a micro level, given the fact that energy wasn't a problem, but it is. Water isn't a problem. 2% of the rainfall in India, if harvested, would suffice 150 liters a person, for 1.4 billion people. And so what are we really doing? And we were sort of, looking at our cities, and we were looking at our buildings, and we had developed this sort of system where our buildings would consume energy and they would consume water and they would generate waste, and it was a one-way flow. What you see on the top here is through this process of sustainability, where our main aim has been to push our projects to net zero energy, net zero water, fresh water, and net zero waste to landfill. Optimization has been mostly about how do you build less? How do you do a lot more with a lot less? And essentially, that's about removing embodied energy, and that's about reducing CO2 emissions from how you build something. Uniqueness is about, again, a set of metrics which looks at tradition, heritage, and culture. And that third philosophy and third arm grows from the fact that across India, given the fact that price points of construction are extremely frugal, everything started looking the same. It didn't matter whether you were in a cold climate, in a temperate climate, in a hot climate, in a warm, humid climate. But by and large, most buildings and everything started looking the same. And that's because they were adopting processes of construction and design that allowed for that to happen. And we found ways of digging into the past to find ways to build the future. And that's where we sort of got the unique. And livability was essentially about engaging not only the client and the end user of our buildings, but trying to engage the people who built that building. Now, when we talk about energy saved, CO2 emission, and fresh water, this is all benchmarked to the ECBC, the Energy Conservation Building Code of India, which is like a green building standard. And based on those standards, all our buildings are under post-occupancy evaluation. And we keep a track of those numbers, of what these buildings are achieving today. But that's over 2.5 decades. So I'll start with the first project. And this project dates back about nearly a decade or so. It's called the Pearl Academy. It sits in Jaipur. Jaipur is in Rajasthan, and it sits in a desert climate. there were many challenges to this project. The first, of course, was the fact that cost. Now, I'm sure a lot of people here don't know, may not be familiar with cost of construction, but this project was built at $200 a square meter with all interiors and all the energy infrastructure, everything all told, which was virtually impossible in that time. And of course, a climate like Jaipur, which goes up to 48, 49 degrees Celsius in the summer, but can drop to close to zero in the nights in winter. And we began thinking about how we are sort of going to be able to build this building. And the first thing that came to our head was to throw out the air conditioning. Because you throw out the air conditioning, along with that, you reduce all the electrical equipment, but more so, you reduce the fact that the power generation is also done locally. So you have these diesel generating sets that generate that power, and you get rid of that as well. And we studied a lot of the traditional architecture. We used computational models to understand how do step wells work, why are they cooler in at the bottom than the top. We understood evaporative cooling, jalis, ventilation, shading. So we mapped out 200-kilometer radius. We said every material that we will use will come from that, because transportation costs are extremely heavy. And the other thing that we discovered at the time was that the temperature of the Earth about 3 meters below the surface is equal to the average temperature of the region. And in Jaipur, like I said, which goes from 0 to 48, 49 degrees, the average was sort of floating around 25. And we said, hey, that's a very useful, and which is why the step wells, if anyone has visited India and they go to the step well and you come down, it naturally feels cooler because the earth banking along with evaporative cooling is a phenomenal cooling mechanism. It's an underground air conditioner, naturally driven. So we said, fine. Now, typically speaking, any institutional building in India would be built as a block, and then you would sort of have the open space, which is the recreation space. But when you're in a desert climate, that open space is really worth nothing. And these large outdoor spaces become mostly unusable through the year. And we said, well, we won't do our building vertically. We'll spread our building out and use the whole building as a shade, like a tree. And therefore, the space under the building will become viable. We did a very optimized, simple rectangular form. Idea was again to decrease the amount of surface area that gets exposed to getting heat gain. And we went through a series of courtyard morphologies. The idea really being to keep the sun out, but let the daylight in. I'm not going to show you these diagrams. All of you probably know them very, very well. But the idea really was to develop, and because it was a design and fashion school, the emotional element was that if you were inside this sort of very rigid form, which was driven by our environmental criteria, in any courtyard, the courtyard should not be sort of like a rectangle and enclosed. It should sort of flow freely like a Mobius strip. And that was sort of the model when we began over about a decade back. To achieve the parameters of, without air conditioning in a desert climate, we sunk down 3 meters. We recycle all the rainwater, and we recycle water from the toilets by filtering and using a treatment plant. And we created our own step well, Bavli, in effect, which allowed for evaporation through the courtyards and cooling the building internally. And that sort of negative space, if I may, was pulled out of the program. So we were supposed to build about 25,000 square meters. We did. We built about 2/3 of that. And that entire area underneath, which to date operates at about 28, 29 degrees Celsius naturally, is used for an outdoor cafeteria, is used for various functions, performances, etc. And that whole underbelly section was designed to do that. These are just some of the pictures of that sort of step well that we created. All the water is harvested. Not a single drop of water leaves the site. But we were just trying to do, just work with limited resources effectively. And obviously, the whole thing sits in shade. It captures the wind flows and it cools the building down. We looked at insulation. Insulation was very critical for a project like this in a desert climate. And there was a local community that made pots. We couldn't afford the sort of very expensive 50 mil glass wool or rock wool insulation. And we thought that pots, which were used traditionally, would make for great insulation, but air is a great insulator. And we use these inverted pots with a layer of screed on the top, and we use that for insulation. The pots were made on site by this local potter community. For the external skin, we kept our window-to-wall ratios very, very optimized. We are at about I think 20 or 25%, providing adequate daylight. And we created this buffer space, which is essentially a service space and a screen. And the screen is made from, again, a set of local community who make cement concrete jalis on a very simple system. And we ran all our services on the outside. So the screen allowed for the fact that the entire windows go blinds free, and the design of the screen changes based on the orientation. And all the services are openly accessible. The sprinklers run here. We use the sprinklers as a facade cleaning system, because once a month they are supposed to test and flush it. So that sort of cleans that up. And that's the building when it was finished about a decade back. So all the materials are still on everything here was from within a 200-kilometer radius. We did achieve the price point. And this building went on to become very popular with various schools of architecture. They've gone and studied it. We've had students from various programs in masters programs studying sustainable design, recording temperatures and seeing it. And for the last decade or so, it is sort of consistently in the summers, when external temperatures have hit 47, it's hit 29 degrees inside without air conditioning. It runs on an energy performance index of about 25 to date. Very simply, we get the bill that just divided out. And whilst it was being built, it gave a certain level of employment to the local community. And that gave us a lot of inspiration. And we thought that, if it was possible to get an 18 degrees delta by passive design, and it was possible to create something in these sort of kind of price points pushed by the adversity of price, then what is it that we could do as we moved on? And that's when we started sort of putting more formal metrics. And which is why I'll jump to a very different kind of building, which is the British School, which is in Delhi. That's a composite climate. And here, budget was not an issue. And our brief was, to begin with, because it was the British School, was that they wanted it to be centrally air-conditioned. All British schools pretty much across the world are either centrally heated or centrally air-conditioned. And we argued the fact that if we can begin to achieve as much as we can, naturally, then we will do so. And this project is about, I think, 6 or 7 years ago. And we then spoke to the clients, which was essentially the High Commissioner and the board, and we said that why don't we look at this 5-acre site and try and do India's first net zero energy, net zero water, net zero landfill, waste to landfill kind of building. And I said, fine, let's give it a shot. And so we did the math on the water, and from the 5 acres of land that we had, I'm not going to go through the calculations, but we could support a population of about 1,300 students. And we said, we'll do this in reverse. We said, so the notion of carrying capacity comes from the fact that what the land can afford in terms of water and energy is all that we will build. And 1,300 students worked very well for them. Now the problem with a city like Delhi is all our rain is concentrated in 3 months. So you can't store that much water for the rest of the year. So what you do is you dig down and you find an aquifer that's pure, and you use that as an underground tank, and you use that as an exchange. So you put water back into it and you pull it out of it. And over the year, you go net zero on water for 1,300 people. We took the same 1,300 people, and then we went about building out how much, because we needed to build about 20,000 square meters for fitting out an IB school. And we were trying to work out what is the correct ratio of rooftop solar to number of levels that we would need to be able to get to net zero, and therefore what would be the target EPI that we need to achieve. And after a lot of to and fro, we came to a 4-story building with a target energy performance index of 56 kilowatt hours per square meter a year. Now, that number would by necessity drive a lot of passive design, where a lot of the heat loads and a lot of the lighting loads would need to disappear. And that's when we would be able to be net zero on water, net zero on energy. And again, we look at a lot of, in Delhi, there's a very old city called Shahjahanabad. We looked at how those morphologies worked, how some of the earth banking worked. The other also key area was safety and security. And because we were propagating the idea of having open corridors and we were not doubly loaded and had them air conditioned, the issue of security, CCTV cameras, and we came up with this idea. We didn't come up. We studied this idea of eyes everywhere. And if you look at any old vernacular evolution of any city anywhere in the world, where there was, in those days when there was no police several hundred years back or CCTV cameras, the cities were designed in a way that there were eyes everywhere. And that really was a security. So a combination of the two factors, we began to look at morphologies where we would be able to get eyes everywhere, step terraces, shaded courts, and we sort of landed up with this sort of model with a rooftop area sufficient to make this into a net zero energy project. Some other small things that we did, we put the labs on the top because the labs are constantly mechanically ventilated because of the fumes, and that automatically creates a buffer for everything underneath. We created natural voids for the wind flows to allow for the courtyards to function properly. And because of the orientation of the site, where we had pushed that form again from like we done earlier, we began to look at the Jali formation. Most of our teaching areas were on the northeast and the northwest, while the southwest was essentially a large screen just shading out the courtyards. A lot of this was built on site, so we came up with this sort of construction methodology of again full windows and having a secondary screen. The screen, of course, varies its opacity and density based on what's behind it and what orientation it works to. And yes, and that's sort of now the completed building. We did a lot of modeling for. So we had the classroom, and that was built. That was done perfectly, but to us, what was more important was to be able to create enough open spaces within which would be comfortable through the year. And we were targeting a delta of about 8 to 10 degrees in perceptible temperature in the outdoor areas in the school as compared to the external temperature. And then here's that project. So that's the front screen that shades off the southwest and sort of creates a full microclimate behind. Again, open corridors. What you see here are air filters because it was a British school. We didn't air condition the entire school, but we did for the classrooms we did, and then create these sort of passive spaces. A lot of outdoor spaces. Now, well, this is a bit old, but the trees are grown now. Yeah, and that's the school. Now, on our post-occupancy, we to date have an EPI of 52. It's the only school in India right now which got a GRIHA 5-star rating. GRIHA is India's own green rating system. And as I am a founding member of the green rating system for, I can say that I had, it is genuine. I didn't falsify any data, but it's operating at a 52. Now, what you see here is a combination of surface temperature and air temperature. So, and then we sort of map that back to perceptible temperature. So at a 44 outside, we did manage to get a 10 to 12 degree delta in all the open spaces inside that school. So to date, and we keep our classrooms at about 26 to 28 degrees. So there is a gradation as one steps out and moves through this entire project. And it operates today as a net zero on all accounts. So that was in that sort of composite sort of climate. I mean, like in a composite climate, the winters aren't a problem. The real problems are, and it's not even the summer because shade, thermal mass, screens, a bit of evaporative cooling, that works. The real problem has always been the monsoon. Why it works really well in schools is that Indian schools are shut in the monsoons. that's the holiday period. And that sort of works really, really well, which doesn't in other kinds of typologies like offices or residential and which sort of brings me to this third one. This is a campus. It's a 100-acre campus for a very large technology ID firm called Wipro. They're amongst the three largest listed companies in India. And they do these sort of really massive campuses, have tens of thousands of people working there. This is located in Hyderabad, in Telangana. It's a very strange sort of climate. It's not very adverse, but it's got a tremendous amount of diffuse radiation. It barely has no cloud cover pretty much through the year. And temperatures do go up, but it's not that high. And it has reasonable wind speeds, reasonable wind temperatures, but the glare is just incredibly high. The diffuse radiation is what pushes temperatures up. And we worked on this project with TransSolar. It's one of the several we've done with them. And this is where we began. So we looked at the site, and that's about 100 acres. It's divided into 3 zones. And that zone 2, as we discovered, was largely unbuildable because it sat in a radius from a lake which wasn't too far away. And even as we discovered, it's sort of a bit low-lying. And the really buildable areas were these 2. We again pursued the idea of a carrying capacity. We had the 100 acres, and we worked out backwards as to how many people can we support from the rainfall. And we then, to store that water, because, like I said, Hyderabad is very strange in the sense that its entire geology is slate rock. So it was very hard to get to an aquifer and do water exchange with. So we really had to build a reservoir. So at a 4-meter depth, we needed about 15 acres of water reservoir to support 15,000 people working there. And again, similarly with energy, we worked out that if we hit a 60 EPI, then we will be able to, with 15 acres of a solar farm, which we have planned over and above the water reservoir. So essentially, the solar farm shades the water from evaporation and picks up the energy. We will be net zero on both accounts. And that's what we really did. So we identified the low-lying area. Everything slopes there. We got the natural rainwater. It's a 15-acre lake, about 4 meters deep. And then it's sort of got the solar panels that sit on top of it and on the site and shade it. And that piece of the land will never get overshadowed. So we could do the solar farm, 15 acres, on the site itself. And that sort of set up the basis of the first series of master plan. The second exercise was, as I'll just go back, was how do we begin to hit a 60 kilowatt hours per square meter per year, of which 25 is on primary energy, which is lighting and air conditioning or ventilation, and the 35 is on equipment. And how do we begin to get our building to work with the 25? The 35 was a given, so that's all internal equipment. The question really was, how do we work to 100% daylighting on the floor plate, and how do we bring our air conditioning requirements down to a point where through the year, and to remind you, these buildings tend to operate about 10 to 12 hours a day, 365 days a year, because they're essentially very large tech companies. So we began this exercise where we did about 8 of them. We did many more, but we sort of isolated 8 morphologies which were built upon isolated single towers, series of square towers, courtyards, a hybrid of the tower and the courtyard, mid-rise high density, low-rise high density, micro courtyards, and we came up with several morphologies heuristically. And then we began to test them. So various kinds of ground coverages, various heights, and we then put them through a series of analysis. So the first analysis that we did was, of course, for wind, because wind was critical for us to, if we were to hit that 60 EPI, which is 25, we also needed to be able to get a lot of the functions from inside the building out. And a lot of the functions to run passively without air conditioning. Of course, where the essential work was happening would be air conditioned for various reasons of, their data centers, they need very tight control on air conditioning, etc. But how much of this could be and for that we needed the wind. Now, predominantly Hyderabad had an east-west wind, and we put all these various forms, we selected 5 that performed reasonably well. We then put them through the horizontal plane. We were trying to look at what, in terms of seasonal solar radiation, would the insolation be on the lower planes. And basis that, we picked up a certain scheme. We then looked at daylight autonomy for each of these 8 or 9 different schemes, and then again began to identify. And this was a highly iterative exercise between wind, solar radiation in the open spaces, and daylighting within the internal spaces, and what morphology would suit it the best. And finally, we selected the option which was sort of the micro courtyard option. And after doing a series of CFD runs on it, we cleaned up the entire the model. Again, this was highly iterative. And if anyone is very good with algorithms, this is a great one for that kind of process. And then we sort of finally ended up. So the first phase is what is now under construction, which I'll take you through. And then we've already done the urban design for the remaining 3, so that, in a sense, the wind flows, the evaporative cooling, the shading, all those parameters remain the same. Coming to that first phase, which is approximately about 1 million square feet, about 100,000 square meters. We began looking at the outdoor spaces, and we went through a series of analysis, looking at a combination of having no roof, no fans, no dry misting, and having only a roof, like a lightweight tensile roof, a combination of roofs and fans, plus dry misting. And we then did a cross analysis of the fact that what would be the financial savings vis-a-vis these spaces sat inside air-conditioned spaces. And that sort of led to this design, which I call a large desert cooler, very traditional large. Desert cooler is essentially what used to be there before air conditioners, a box with a fan, and you had these this sort of hay on the side where water ran down, cooled it and shoved it through. And so the entire plane, which sort of sits on an elevated podium, was designed for those wind flows and those outdoor spaces. And we worked with SBP. We got this sort of height with this sort of tensile roof in combination with Transolar and us, and we sort of got this entire outdoor space working in a way that it is comfortable through the year. So it's comfortable for rain, it's comfortable for the summer, it's comfortable for the winter. And by and large, this entire outdoor space now takes on primary functions. I won't spend too much time on the indoor spaces. We went through a similar exercise of looking at various kinds of mechanisms of how can we remove as much air conditioning from the inside, whether it's underfloor, with heat recovery, hybrids, low velocity fans, and came to an optimal solution. Again, a lot of this is very cost-based, but it's also but it's a combination of sustainability and cost. And of course, settling for the fact that our client agreed to an internal temperature of 28 degrees, which was very useful because, and it's actually correct, because external temperatures can go up to 38 to 40 degrees, and working out the whole system based around that. So when we finished the design, 56% of the area was in under air-conditioned space, but consuming about less than half the air conditioning. So typically speaking, in this region, a building would consume 250 square foot for 1 ton of air conditioning. This project is operating at about 650 square feet per 1 ton of air conditioning. So even though 56% of the spaces are air conditioned, they're consuming less than half. About 35% have been moved to natural ventilation. Now, when I say natural ventilation, and I say the third piece, which is shaded outdoor, all of these are achieving thermal comfort conditions through the year. Greater than 90% of thermal conditions through the year. So not only did we manage to get about 10% of that area outside, which is about nearly 10,000 square meters. So cafeteria, gym, recreation, library is in that outdoor shaded space that I was showing you. We have outdoor meeting rooms, which were removed from the inside area, and of course, the rival plaza. And in the naturally vented spaces, we have various other functions. So effectively, only half the building is air conditioned. And this typically would be at 100%. Okay, so dramatically different project. I mean, this sits in Kolkata, which is the extreme sort of the extreme east of India. It's got a warm, humid climate, extremely humid, and temperatures don't change very much through the year. It's very close to the sea, but it's also in some senses, the cradle of civilization. A lot of the first universities, the first art, knowledge, culture, music, a lot of that was born in this part of the world, in this city particularly, and we began looking at the site. Now, I think the total area here is about 3 million square feet, if I'm not wrong. Yeah, about 300,000 square meters, and it's a 17-acre site. Now, we did the math on this. We couldn't push this one to net zero because, like I mentioned earlier, any environment that is high humid, the city maintains a greater than 70% humidity pretty much through the year. And therefore, in a mixed-use environment consisting of offices, hotel, conferencing, data centers, etc., the air conditioning was inevitable. However, what we started thinking about was what could we do in terms of the entire site, and therefore we set up a site plan where we could maximize the wind flows through the site, and all the buildings. What we did here was because Calcutta sits on a 22 degrees latitude, which is pretty much the tropics, but we tilted the buildings 22 degrees to pure north. And what that allowed us to do was essentially shade from one side. Because when the sun overshoots, you end up shading from two sides, and it led to a 25% reduction in solar exposure. We found this this very interesting. But every time you tilt a building towards the east from pure north, by the latitude the building sits at, it actually helps cut down It helps cut down solar exposure naturally, which helped reduce the amount of shading we had to put into the building in the first place. Then once we sort of had that sort of east-west axis, and we left a lot of cross axes as well, because we wanted a lot of natural ventilation. Wind speeds are not very high in Calcutta. They're at about 2.5 meters per second, but over the year, they changed direction. And which is why we sort of had to have this sort of thing sort of very free and as opposed to the previous one that I showed you, which was very fort-like, but very channeled. This had to be sort of very open and transparent. I'm going to go to the landscape design of how that sort of works with the wind flows. The second problem that we had was a lot of this was very large flow plates, 40, 50,000 square feet flow plates. And by and large, what happened to large flow plates traditionally in these kind of is that you get these sort of very deep 60 by 60 or 50 by 75 meter deep flow plates, and your daylighting drops to on a CDA or if you're doing daylight autonomy, or it drops to anywhere between 40 to 50%. And we took the same area and we changed the morphology of the building so that we could push that back to about 90 to 100%. And I mean, the point really about that is the fact that you don't really have to work with the form, which is a given. But if you go iterative, the same exercise allowed us to break this up into where we put our core and how the form sort of breaks up where we get 100% natural daylighting. So that was sort of the final piece of design when we finished up, I think, about 2.5, 3 years back. It's been in construction ever since. So we then began to look at the fact that now that we had a microclimate on the site, as you can see, this all reasonably well shaded, it's well ventilated. We now started working with a lot of the local craftsmen. And that sort of goes to my earlier point about, how do we work with local communities? And we found a lot of this sort of tradition, art, knowledge, culture. So we treated the entire 17 acres of the site as an open air sculpture and art gallery. Naturally ventilated, naturally water protected, 17 acres of outdoor, if I may, an arts and crafts museum. We worked with a lot of the local art schools and the local craftsmen who have this incredible craft who make all these sort of sculptures. And we then used a lot of the traditions of Bengal, of Calcutta, and abstracted them into this sort of graphic artwork, which the artisans could work with. And we then started using the west and the east facades, because all our buildings were north-south, albeit turned 22 degrees, and started working with them into sort of creating this urban art form, where it, of course, it provided great amounts of insulation, because they were just carving local stone, and we were working with that. And of course, working with the local alphabet, and again, working with the stone. And coming up with this sort of 500 meter by about 100 meter long urban art facade. This is all west. And a lot of this sort of being crafted by local craftsmen. And again, on the other side, on the east as well. So that's the project, again, under construction, where a lot of this, again, is being done on site. And this we've done sort of as a very, very deliberate move in terms of trying to, these are dying communities. Craft communities are dying communities. And I think the more we work with them, the more we learn from them. They seem to have a better heuristic understanding of what we understand computationally. And this entire sort of 500 meter by 100 meter high urban facade is being put up by these local craftsmen, and eventually sort of leading to that on completion. So we managed to get in a very, very humid environment. We got an EPI of 43 by a lot of these measures. So we are 90% daylit, zero glare, which is critical, because what you really don't want to do is draw the blinds if you get the glare and then switch the lights on and it all goes south. So glare-free, 90% daylit, window-to-wall ratio at 25%. Our facade is at 1 watt per square foot, envelope load design. And of course, the entire site is fully ventilated. Then that's how we sort of managed to hit the 43 degrees. And even in a humid environment, we've got a 5-degree delta in perceptible temperature. So at a 36 degrees to a 31 with ventilation, it works really well, even when you won't stand there on the site even today. And I think I'm going to sort of, in the interest of time, I'm going to do this last one. It's a precious project. We finished this, and it's precious because it was done during the COVID times. It just finished recently, a few months back. And this was a project that came to us about a year and a half back, pre-COVID. And it sits in a remote area in the hills in Uttarakhand. I'm just very quickly going to go to a picture. That's the site. There is no power cable. There are no drains. There is no water. There's water, but there's no water supply and a lot of the community that lives here actually makes this product. Now, Forest Essential is a luxury global brand, is an Ayurveda brand of beauty product. And a lot of that is, and a lot of the people who make that product live here, and they walk or they travel about 20, 30, 40 kilometers to the town below to work there. And when the client came to us to redo that factory, and we said, why don't we build something here where they live, where they can work? And they said, but no infra. And our site is actually down there. And this is sort of very broken road. And we didn't have a road leading to where they had the piece of land. And we went there and pre-COVID, and we looked at the community, we looked at all the local materials, we looked at how they live, and we found a very high level of resilience. And in that 1 kilometer radius from that site, we found about 800 people. There were about 150 hutments. And we said, fine, we're going to build this here. And we had a great client who agreed. And of course, it had to be completely off-grid. But also because we didn't want to get no material could come here. There was no road bringing trucks of material up here. So we built with very, very simple form. A lot of it was driven by what local materials we had. Courtyard, south-facing for the solar panels, and then a secondary terrace for drying some of the Ayurveda stuff. Naturally ventilated, all driven, standard, good passive principles of design. Nothing very, very innovative, but easily buildable. Of course, we did a lot of studies pushing down the window-to-wall ratio. So glass was the one material that we had to get from a remote town. And we went through a series of exercises from the base case, which was the vernacular, and the fact that we were going to put a production factory making these Ayurveda luxury products that are exported to New York and London and Paris and are in shops on the high street. And essentially, that was a sort of finished section where, because of course it gets very cold in the winters, it's high in the hills, it's warm in the summer, and we sort of managed to get through the year a reasonable level of humidity and temperature control purely passively. More importantly, it was entirely built by the people who work here, by the community of people, and the architecture and the materials were all based around that. We learned a lot more about passive design from them, of how to handle this in winters and summers, how to harvest the water, reuse the water. And that's sort of the project sort of sitting sort of off-grid, isolated. Of course, it's net zero, it's energy positive now, but and it's energy positive and supplies some power to some of the hutments as well. That's the factory now in use, low velocity fans, windows open, natural daylight. There's a community that's a project by the community, for the community, built by them, supplying a product to the global world. And that's setting up there. It's used as a school in the evening by the same community. And yeah, and that's it. It's just sort of a two-decade history of a variety of projects across various climates and various challenges. But at the core of it has always been the same principle. We begin by thinking, what if there is no energy and water? What do we do? How do we build? And of course, you will consume. So get as much equipment out of the building, get rid of the air conditioning as much as you can, reduce your heat loads, work as much as you can with local materials, with the local communities. And that's what will give character and identity, and hopefully will lead to an architecture of resilience. So that's it. Thank you very much.